So, what if I told you the reason cancer so often beats the immune system isn't, it isn't because your immune cells are weak.
Right.
It's actually because they are quite literally worked to death. I mean, imagine an elite, heavily armed security force inside your body.
Yeah, your key cells.
Exactly. Now drop that force into a battlefield where the enemy just never stops attacking, 24 hours a day for months. Eventually, those elite cells don't just get tired, their internal programming completely shatters.
They drop their weapons.
Right. They drop their weapons, they stop communicating, and they just give up. And in the oncology world, this is called T-cell exhaustion. It is the single biggest roadblock preventing immunotherapies from curing more patients today.
It really is. I mean, it is the defining bottleneck. Because when T cells exhaust, incredibly advanced treatments, things like CAR T-cell therapy or immune checkpoint inhibitors, they just hit a brick wall.
Because the cells themselves fail.
Exactly. The drugs might be perfect, but if the cells have surrendered, the therapy fails.
Which is why today's deep dive is so critical for you to hear. We are looking at a really groundbreaking 2026 review from the journal Trends in Cancer, and our mission today is to uncover the hidden rulebook that forces your T cells to shut down.
We're going to look right under the hood.
Right, at the epigenetics, the epitranscriptomics, and the cellular metabolism that drive this whole collapse.
Yeah, we can trace this breakdown layer by layer. So we'll start with the physical hardware of the cell, which is the DNA epigenetics. Then we'll look at the software, the temporary RNA messages, or epitranscriptomics.
Which is a mouthful, but we'll get there.
We will. And from there, we dive into the metabolic power supply, running the whole operation. And finally, we'll look at how clinicians are actively hacking these three layers right now to reinvigorate exhausted cells in real patients.
Okay, let's unpack this. Because before we can start hacking exhausted cells, we really have to understand the environment that breaks them in the first place. The sources describe this battlefield as the suppressive tumor microenvironment, or TME.
The TME is just a remarkably toxic space. When T cells infiltrate a tumor, they face what we call chronic antigen exposure.
Meaning they're always on.
Right.
Yeah.
Normally, a T cell fights a virus, it clears it, and it rests. But a tumor is always there. It's constantly triggering the T cell's alarm bells. And over time, this relentless stimulation forces the T cell down a very distinct differentiation trajectory.
It changes them completely.
It does. It loses its polyfunctionality. That means it can no longer deploy multiple immune weapons at once. It loses its ability to clone itself, and it loses its memory potential.
And I was reading that this shift, it isn't just behavioral, right? It's an actual physical rewiring of their genes.
Absolutely.
Like the genes that give a T cell its memory and stem-like qualities, things like TCF7 cell, IL-7R, they are forcibly shut down.
Good.
While at the same time, specific exhaustion genes are permanently locked into the on position.
Yes, genes like PD1, LEG3, TIM3, and CTLA4, when those lock on, that physical rewiring creates this sort of one-way conveyor belt of exhaustion.
And the review breaks this down into subclasses, right?
It does. It begins with cells we call precursor exhausted T cells, or TPEX. At the very start of the belt, you have TPEX1 cells. These are highly stem-like. They hold immense regenerative potential.
But then they move down the belt.
Right. As the chronic stimulation continues, they differentiate into TPEX2. They can still multiply, but they've lost some of that crucial self-renewal capacity.
And if they stay in that toxic tumor environment too long, they cross a point of no return.
Exactly. They become terminally exhausted cells, or TTEX.
First TEX1 and finally TX2.
Yes. And those just accumulate helplessly inside the tumor as it progresses. They're entirely unable to fight.
So if we use a sports analogy here, the TPEX precursor cells, those are your reserve bench. They are resting, they're capable of training, and they're ready to be called up to fight.
That's a great way to look at it.
And the terminal TechX cells, those are the burned out frontline players who have just permanently quit and won't get back on the field.
Which is exactly why that reserve bench is clinically vital. The data shows that durable long-term responses to things like CRT therapy, they rely almost entirely on preserving those flexible plastic TPEX cells, not the fixed terminal ones.
Okay, but hold on. Let me play devil's advocate for a second. If those terminally exhausted frontline cells are just permanently broken by fixed DNA changes, why do researchers even care about them? I mean, shouldn't we just design a therapy that pumps out millions of the TPEX1 reserve cells and completely blocks them from ever stepping onto that conveyor belt?
That's a really common question, but what's fascinating here is the biological necessity of differentiation. You cannot kill a tumor with a reserve bench.
Oh, because they're just sitting there.
Right. Those progenitor cells must eventually mature and differentiate into effector cells to actually deploy their toxic payload against the cancer.
Yeah.
If you completely block that transition, you just have this massive army of highly functional stem cells that never fire a single shot.
Wow, okay.
So the goal of modern immunotherapy isn't to stop differentiation. It is to master the balance. You have to preserve the reserve pool so it doesn't empty out, while still allowing enough cells to march forward, fight, and then inevitably exhaust.
Okay, let's do a quick recap so we're all on the same page. Bullet 1, exhaustion is driven by chronic exposure in the tumor microenvironment. Bullet 2, stemness genes turn off and exhaustion genes lock on. And bullet 3, TPEX reserve cells can still be saved and are crucial for therapies, while TTX cells are basically a dead end.
Perfect summary.
So if I'm tracking with you, the tumor forces this one-way trip from the reserve bench to the burnout ward, and we have to somehow slow that conveyor belt down without stopping it entirely. Which brings us to the actual hardware enforcing this. The paper dives deep into the epigenome.
Yes, the epigenome. This is the structural layer sitting physically on top of the DNA. So every cell in your body has the same master DNA blueprint, but the epigenome dictates which sections of that blueprint are unspooled and readable and which are tightly coiled and hidden away. And it does this using a few mechanisms, starting with DNA methylation.
Which basically acts like a physical padlock on the DNA, right?
Very much so. You have an enzyme, for example, DNMT3A, and it literally attaches a chemical methyl group to specific cytosine residues on the DNA strand.
And when it does that to the memory genes, it locks them away.
Exactly. When it padlocks those genes responsible for T-cell memory, the cell is forced further down that exhaustion conveyor belt. But researchers have found a way around it.
By knocking it out.
Right. By genetically knocking out that specific DNMT3A enzyme, they generated core RT cells that heavily resist exhaustion. Those edited cells maintain their attack by ramping up survival signals, specifically IL-10 signaling.
That's amazing. And it's not just the DNA strand itself getting locked, is it? Because the DNA wraps around these protein spools called histones, and those spools can be locked up too.
Yes, through histone modifiers. So an enzyme called SUV39H1 places a repressive mark on these spools, specifically an H3K9E3 mark, which tightly packs the DNA away.
And deleting that helps.
Massively. Deleting that specific enzyme in the lab has dramatically improved tumor control across leukemia, prostate, and lung cancer models.
Wow. And there's another major player mentioned, EZH2, which places a different repressive lock.
Yes, the H3K27MED3 mark, EZH2, is part of the PRC2 complex.
Right. And the review mentioned EZH2 gets triggered by something called tonic signaling. From what I understand, this happens a lot in engineered CAR T cells where the artificial receptors constantly misfire. It's like the cell is sitting in neutral but redlining its engine 24/7.
That's a great analogy. Constant redlining leads to rapid burnout. But clinicians found an ingenious workaround for this.
The dasatinib, right.
Exactly. By administering a leukemia drug called dasatinib, they can temporarily shut down the CRT cell signaling cascade. It gives the cell a transient rest.
So by turning the engine off temporarily, EZH2 never gets the signal to lock away the memory genes.
Yes, and the cell preserves its stem-like state.
That is so clever. And beyond the locks, the cell also has these massive architectural proteins, right? Chromatin remodelers like the Swiss-Olaus complexes.
Yeah, BAF and PBAF and IL-80.
Right. They physically shove the histone spools around to open or close entire neighborhoods of DNA. And you also have non-enzymatic scaffolds like ASXL1. And then you have the transcription factors. I like to think of them as the foreman reading the blueprints.
The foreman, yes. You have activators like FXO1, MYB, BACH2, CJUN, and BATF. These promote that pristine reserve state. And then you have repressors like CNF217, KLF2, and MED12 that limit memory.
And tinkering with those foremen has very real-world consequences. The review details a human phase 1 clinical trial where scientists engineered FARA T cells to artificially overexpress the activator CJUN to treat acute myeloid leukemia.
Right, the AML trial.
The cells fought aggressively, but there was a massive safety warning. One of the patients experienced grade 4 toxicity. It really highlights the stakes here.
It does. When you go in and permanently alter the physical DNA hardware, whether you are deleting epigenetic locks or permanently supercharging an activator, the effects are profound and sometimes uncontrollable. Once that edit is made, you cannot simply undo it if the immune system becomes too aggressive.
So to help everyone remember this hardware layer, I came up with a mnemonic. LARL is for locks, like DNA methylation and DNMT3A. A is for architects, the chromatin remodelers, like Swiss IS and F. And R is for repressors and activators, the transcription factors.
I like that. Locks, architects, repressors.
Okay, 10-minute recap. Bullet 1, DNMT3A and histone modifiers physically lock away memory genes. Bullet 2, tonic signaling forces exhaustion, but resting cells with drugs like dasatinib can reverse it. And bullet 3, transcription factors act as the gas and brakes for stem-like phenotypes.
Got it.
So if permanently messing with the DNA hardware is too dangerous, there has to be a safer way to rewrite the rules, which is a perfect transition to the next layer of this biological rulebook. We move from the permanent hardware to the temporary software. Welcome to epitranscriptomics.
Epitranscriptomics. Even if the DNA blueprint in the nucleus is wide open and readable, the cell still has to transcribe that information into an RNA message to actually build anything.
Right.
So epitranscriptomics is the placement of dynamic, reversible chemical modifications directly onto those temporary RNA messages.
My favorite analogy for this, imagine a shared live Google Doc. The master DNA blueprint stays safely locked in the vault untouched. But the working copy, the RNA, is actively being edited by a whole ecosystem of programs.
Yes, the writers, erasers, and readers.
Exactly. You have writers that type critical instructions into the doc, erasers that delete them, and readers that scan the doc to decide if it should be published to the cell or immediately sent to the trash.
And the most heavily studied instruction they type out is a mark called M6A. The writer for this mark is a complex made of MET-TL3 and MET-TL14.
And why is that one so important?
Placing that M6A mark on an RNA message is absolutely essential for T-cell survival, primarily because it regulates a family of genes called SOCS. If a T-cell loses the MET-TL14 writer, it becomes deeply, irreversibly dysfunctional.
Wow.
The importance of this is so clear that targeting this pathway is already in clinical trials for solid tumor therapies like TILs.
And there are other marks too, right? Like M6AM placed by PCI1 and M5C placed by NSUN2, which is needed for Th17 differentiation.
Yes, and AC4C placed by NET10. The system is incredibly complex.
But the erasers and readers are just as powerful as the writers. There is an eraser called FTO that actively removes M6A marks to suppress a gene called FAS.
Right, and suppressing FAS essentially prevents the T cell from undergoing programmed cell death. So it helps higher T cells survive significantly longer.
And then there is a reader protein, YTHDF2.
That reader pushes T cells toward a highly specialized state called Th9 differentiation. And what makes that fascinating is that researchers found this exact Th9 signature heavily enriched in leukemia patients who had achieved remarkable 8-year-long remissions.
That is incredible, 8 years. But I have to push back here. We have CRISPR technology. We can go straight into the nucleus and edit the master blueprint, the core DNA epigenome. Why are scientists spending so much time messing with these temporary RNA Google Docs? Isn't it just overcomplicating the engineering?
If we connect this to the bigger picture of how immunity functions, the answer really comes down to speed and safety.
How so?
An immune cell needs to respond to a rapidly mutating tumor in minutes, not days. Editing the RNA layer allows for rapid, fine-tuned, and entirely reversible responses.
Well,
You can change how the cell behaves in real time without ever risking a permanent, potentially dangerous mutation to its genetic hard drive.
Which brings us back to avoiding that grade 4 toxicity we saw in the AML trial. Okay, quick 15-minute recap. Bullet 1, epitranscriptomics uses writers, erasers, and readers to dynamically alter RNA. Bullet 2, the M6A modification is crucial for survival, targeting genes like SOCS and FAS. And Bullet 3, editing RNA offers a temporary, flexible way to boost T-cell fitness. So we've got the hardware padlocked by epigenetic enzymes, and the software being constantly rewritten by RNA writers and erasers. But none of these enzymes work for free. What is actually powering this massive construction site?
This is perhaps the most profound twist in the entire review. All of those complex enzymes, the hardware locks and the software writers, they are entirely dependent on the cell's metabolism. The metabolic fuel dictates the genetic software.
That completely flips how I used to think about cellular energy. Metabolites aren't just calories burned for movement. They are the literal chemical building blocks that the enzymes use to modify DNA and RNA.
Let's trace the physical pathway to show how. Methylation, whether it's padlocking the DNA or placing an M6A mark on RNA, it requires a chemical methyl donor. Inside the cell, that donor is a molecule called SAM.
Which stands for S-adenosylmethionine.
Right, and SAM is synthesized directly from the amino acid methionine.
But here's the problem. In the tumor microenvironment, the rapid-growing tumor cells aggressively consume almost all the available methionine.
They literally starve the immune system. Exactly. Without methionine, the T cell cannot produce SAM. Without SAM, the epigenetic locks fail, the RNA writers have no ink, and the entire regulatory network collapses. The cell exhausts not because it forgot how to fight, but because it has been deprived of the raw materials needed to read its own survival blueprints.
And the same starvation tactic applies to the spools, the histones. To open up memory genes, enzymes need to attach acetyl marks, which requires a fuel called acetyl-CoA.
Yes, sourced via enzymes like ACSS2 or ACLY.
Right, establishing this literal acetate to citrate metabolic switch. But the tumor doesn't just starve our troops of good rations, it actively pumps the battlefield full of toxic smoke.
Those are oncometabolites. As a tumor metabolizes, it secretes waste products that directly poison the T cell's epigenome. For example, tumor cells release large amounts of succinate and fumarate.
And what do those do?
These byproducts structurally mimic a vital molecule in the T cell called alpha-Kg. So the toxic waste competitively jams up the alpha-Kg-dependent enzymes like the TEP enzymes that maintain healthy DNA states. It acutely suppresses the T cell's ability to function.
But the detail that absolutely blew my mind was about a metabolite called ataconate.
Well, ataconate is fascinating because it doesn't even come directly from the cancer cells.
Right.
It is secreted by tumor-associated macrophages, which are immune cells that the tumor has basically brainwashed into protecting it. The ataconate enters the T cell through a specific transporter, SLC13A3, and shuts down those vital TEI enzymes, driving severe EOMAS-associated exhaustion.
But here is the massive aha moment. The paper highlights that this incredibly complex macrophage-driven exhaustion mechanism can be partially reversed by ibuprofen.
Yes.
I mean, a common over-the-counter NSAID that you probably have in your medicine cabinet interacts directly with cutting-edge cancer metabolism to rescue T cells. That is wild.
It really highlights how deeply interconnected systemic inflammation and cellular metabolism really are. And another ubiquitous byproduct is lactate.
Lactic acid.
Tumors are infamous for producing massive amounts of it. That lactate enters the T cell and directly alters its chromatin through a newly discovered process called histone lactylation.
But we can block it.
Yes. If scientists take those T cells into the lab and temporarily block lactate production using an LDH inhibitor before giving them back to the patient, those cells become incredibly potent stem-like fighters.
Okay, final recap time. Bullet 1, epigenetic and RNA enzymes are totally dependent on metabolic fuel like SAM and acetyl-CoA. Bullet 2, tumor environments starve T cells of good metabolites and pump out toxic ones like ataconate and lactate. And bullet 3, transiently blocking these metabolic pathways can drastically reprogram T cells.
That sums up the biology beautifully.
So if we step back and synthesize everything we've uncovered, the tumor starves the T cell of essential fuel like methionine. It floods the environment with toxic waste like ataconate and lactate, which in turn paralyzes the RNA software and permanently padlocks the DNA hardware. It is a beautifully terrifying multi-layered defense system.
It really is.
So how on earth do we safely bypass all 3 layers to actually help a patient in the clinic?
By using functional extensions of these states, such as engineered cytokines, to rewrite the metabolic environment.
Like giving them a supply drop?
Exactly. For instance, engineering a cell to secrete IL-10 forces its metabolism to utilize oxidative phosphorylation, generating energy far more efficiently in a starved environment. Interleukin-4, or IL-4, revitalizes exhausted cells by boosting their glycolysis pathways.
And we are already seeing staggering clinical wins from this. The review highlights a trial using CD19 CAR T cells that were engineered to secrete IL-18. They gave these to lymphoma patients who had already failed multiple prior therapies, patients with very few options left.
And the results were incredible.
Those IL-18 secreting cells achieved an 81% response rate at 3 months.
It's a true testament to the power of hacking the microenvironment. But the review concludes with a vital safety roadmap for the future. As we discussed earlier, permanent genetic deletions are risky.
Like the grade 4 toxicity.
Right. If you permanently knock out regulatory genes like TET2 or DNMT3A, you risk creating a T cell that never stops dividing, which has historically led to antigen-independent clonal expansion and secondary lymphomas in patients.
Which means the future of precision medicine lies in transient, temporary control.
Precisely. Clinicians are moving toward pharmacological inhibitors. like using tazemetostat or valemetostat to temporarily block EZH2, or using advanced RNA-based engineering like CRISPR and CRISPR.
And those don't cut the DNA.
No, they can silence a target gene for roughly 30 days without ever cutting the underlying DNA strand.
They are even designing tumor-restricted promoters like NR4A2 and RGS16. They program the CAR T cell so the therapeutic payload, the aggressive activator or the cytokine, stays completely dormant while circulating in the blood.
Yes.
It only turns on when the T cell physically senses the toxic tumor environment.
It's the ultimate failsafe, ensuring the extreme power of the engineered cell is unleashed only where it's needed.
So what does this all mean for you listening right now? If you take anything away from this deep dive, it's that T-cell exhaustion isn't a passive process of a cell simply getting tired. It is a highly regulated, interconnected network. You have the DNA locks representing the permanent hardware, the RNA modifications acting as the dynamic software, and the metabolic currency running the power supply.
And by understanding how these three pillars interact, researchers aren't just fixing broken cells. They are programming the ultimate cancer-killing machines.
Exactly.
This multi-layered understanding completely reframes our clinical approach. Right now, almost all of our therapies are reactive. We wait for a patient to get sick, we wait for their T cells to exhaust, and then we try to rescue them.
Right after the damage is done.
But by decoding the exact metabolic and epigenetic triggers, it raises an entirely new frontier. What if we could be proactive? What if we could preemptively vaccinate or nutrient load an individual's immune system? We could prime their epigenome so that their T cells simply refuse to read the tumor's exhaustion signals in the first place.
Preemptive metabolic armor. I absolutely love that. So I will leave you with this thought. If you were the one designing a SAR T cell to save a life tomorrow, would you risk a permanent DNA edit for a potentially unstoppable attack? Or would you play it safe with a temporary RNA sticky note?
It's the defining question.
It really is the defining question of the next decade of cancer immunology. Think about it, keep exploring, and thanks for joining us on this deep dive.